What if I told you that everything you learned about matter in school was, well, not exactly a lie, but like getting only the first chapter of an epic sci-fi novel? Those three states of matter, solid, liquid, and gas. That's like saying there are only three types of stars in the universe. Today, we're diving into the mind-bending reality of matter, the weird, the wonderful, and the downright impossible states that exist throughout our cosmos. And trust me, by the end of this video, you'll never look at a cup of coffee, a star, or even empty space the same way again. But before we get started, hit that subscribe button if you're ready to have your mind blown about the universe on a weekly basis. And stick around until the end, where I'll show you something about matter that literally defies gravity. Seriously. Okay, let's start with the basics, but I promise we won't stay basic for long. We all know solid, liquid, and gas. The ice in your freezer, the water in your glass, and the steam from your shower. Pretty straightforward, right? But here's where it gets interesting. What controls these states isn't just temperature, it's energy. See, what we call heat is actually just atoms partying. The hotter something is, the more those atoms are bouncing around like they're at a cosmic rave. When I touch this coffee mug, ouch, still hot, what I'm feeling is literally billions of molecules slam dancing and transferring their energy to my hand. And when we cool something down, we're basically telling those atoms, hey, party's over, time to chill out. At absolute zero, minus 273.15 degrees Celsius, the party completely stops. No movement, no vibration, nothing. Now, fun fact, we've never actually reached absolute zero in any lab. We've gotten incredibly close, just billionths of a degree away, but never all the way there. It's like trying to reach the speed of light. Physics just says, nope, not happening. But here's where things get wild. Between those classic states and beyond them exists a whole universe of exotic matter that would make your high school science teacher's head explode. Let's talk about plasma first, the forgotten fourth state of matter that actually makes up 99% of the visible universe. Every star, including our sun, is basically a giant ball of plasma. But what exactly is it? When you heat a gas to ridiculous temperatures, something dramatic happens. The electrons get ripped away from their atoms, creating a soup of charged particles that behaves nothing like a regular gas. It conducts electricity, responds to magnetic fields, and can even organize itself into complex structures. Those gorgeous aurora lights dancing in the polar skies, that's plasma putting on a light show when solar wind hits our magnetic field. And get this, you can actually create plasma in your kitchen. Yeah, that's right. Disclaimer, please don't actually try this because it could damage your microwave. But if you put two grape halves next to each other in a microwave, the electromagnetic waves get concentrated between them and create a tiny plasma arc. It's like summoning a miniature star in your kitchen. Science is wild, right? But temperature isn't the only player in this cosmic game of matter states. There's another critical factor, pressure. Here's something that absolutely blew my mind when I first learned it. Without pressure, liquids wouldn't even exist. In the vacuum of space, matter is either solid or gas, nothing in between. The only reason we have beautiful oceans, rainfall, or blood flowing through our veins is because Earth's atmosphere exerts pressure. Isn't that crazy? Something as fundamental as liquid water, the basis for all life on Earth, only exists because we have an atmosphere. If you could somehow stand on an airless moon with a bottle of water and open it, the water would instantly boil away into vapor, even if it's freezing cold. That's why finding liquid water on other worlds is such a big deal. It means conditions there are at least somewhat Earth-like. And this isn't just some academic point. This principle is used all the time in the real world for a process called lyophilization or freeze-drying. Ever had freeze-dried ice cream or instant coffee? They freeze the original product, then place it in a vacuum chamber where the frozen water skips the liquid state entirely and goes straight to gas. No heat required. The pharmaceutical industry uses this all the time to preserve medicine that would be damaged by heat. Now let's get into the really mind-bending stuff. When you combine extreme heat and extreme pressure, you get something called a supercritical fluid. Imagine a substance that flows like a liquid, but expands to fill space like a gas. It can dissolve things like a liquid, but penetrate tiny spaces like a gas. It's like the superhero of matter states. It has all the powers. If you could see inside a pressure chamber with liquid CO2 on the bottom and gaseous CO2 on top, as you crank up the heat and pressure, something bizarre happens. The boundary between them doesn't boil away. It just vanishes. The distinction between liquid and gas literally stops existing. This isn't some lab curiosity either. Supercritical CO2 is used to decaffeinate coffee and extract essential oils. And deep inside Jupiter, hydrogen exists in a supercritical state that's neither truly liquid nor gas. But that's nothing compared to what happens in the quantum realm. When helium is cooled to just 2 degrees above absolute zero, it becomes a superfluid. This stuff behaves like something from a sci-fi movie. It flows with absolutely zero friction. If you put it in a cup, it would spontaneously climb up the walls and spill over the edge, completely defying gravity. The first time I saw a video of this in college, I was convinced it was fake. But nope, it's completely real. It's quantum mechanics taking over at a scale we can actually see with our naked eyes. And it gets weirder. In 1995, scientists created something called a Bose-Einstein condensate. Imagine cooling atoms so extremely that thousands of them start behaving like a single giant superatom. They move in perfect unison, as if they're one entity. Matter stops behaving like particles and starts acting like waves. The scientists won the Nobel Prize for creating this state, and get this, Einstein predicted it would exist way back in 1924, decades before we had the technology to create it. Speaking of intense conditions, let's talk about what happens inside dying stars. When massive stars run out of fuel, they collapse under their own gravity. The pressure becomes so intense that electrons get squeezed closer and closer together. Eventually, they fight back through something called the Pauli exclusion principle. Basically, electrons refuse to occupy the same quantum state. This creates electron-degenerate matter, the stuff of white dwarf stars. It's so dense that a teaspoonful would weigh several tons on Earth. But for really massive stars, the collapse continues past this point, forcing electrons to combine with protons and form neutrons. The result? Neutron stars, essentially atomic nuclei the size of cities. These are so incredibly dense that a sugar cube-sized portion would weigh about 1 billion tons. The gravity at their surface is so intense that they bend light significantly. Can you imagine that? Matter so dense that light itself bends around it? The universe is absolutely bonkers. But the award for most exotic state goes to Quark-Gluon plasma, the primordial soup that existed just microseconds after the Big Bang. Under normal conditions, quarks, the building blocks of protons and neutrons, are bound together by particles called gluons. But at temperatures of several trillion degrees, these bonds break and quarks and gluons float freely. We've actually recreated this state at the Large Hadron Collider by smashing heavy ions together at nearly the speed of light. For just the briefest instant, we create temperatures hotter than the center of stars, allowing us to glimpse what the universe looked like in its first moments. Think about that. We're literally recreating the conditions of the early universe in a tunnel under Switzerland. If that doesn't blow your mind, I don't know what will. Now here's something to really ponder. Everything we've talked about, all these incredible states of matter, make up less than 5% of the universe. The rest consists of dark matter and dark energy, which we can observe through their gravitational effects, but don't fully understand. What exotic states might these mysterious components exist in? We simply don't know yet, and that's what makes this field so exciting. Did you know that some theoretical physicists believe there might be entire stars made of exotic matter? Strange stars, made of strange quarks, might exist throughout the galaxy. Or imagine neutron stars so massive they collapse into a quark star instead of a black hole. I know. At this point it sounds like I'm just making stuff up, but this is actual cutting-edge astrophysics. The universe is stranger than we can imagine. So why does all this matter? Why should we care about exotic states of matter? For one, understanding these states helps us comprehend the universe's most extreme environments. But there are practical applications too. Superconductors, materials that conduct electricity with zero resistance at low temperatures, could revolutionize energy transmission if we could make them work at room temperature. Imagine power lines with no energy loss whatsoever. And each new state we discover challenges our understanding of physics and pushes science forward. The same principles we discover studying superfluids help us understand black holes and neutron stars. I think what I love most about this subject is how it reveals the interconnectedness of our universe. The same fundamental physics that governs particles in a lab also shapes the behavior of stars and galaxies. Nothing exists in isolation. It's all connected by the same beautiful physical laws. Remember that gravity-defying thing I promised at the beginning? Check this out. That's superfluid helium climbing the walls of its container against gravity. If that doesn't make you fall in love with physics, I don't know what will. So next time you're sipping a drink or holding an ice cube, remember, you're just scratching the surface of what matter can do. The universe is filled with states of matter so bizarre, they make science fiction look boring. If this video blew your mind half as much as researching it blew mine, smash that like button. And if you want more mind-bending space content every week, hit subscribe and that notification bell. And don't forget to leave a comment telling me which exotic state of matter you found most fascinating. I'm super curious to hear what grabbed your attention. Until next time, keep looking up and stay curious. The universe is way weirder than they taught us in school. Adios.